So what I'd really like to do, let me start again. So of all the videos I've been involved with for 60 Symbols and Numberphile and Brady's million other channels, the one I'm least happy with by far is the one we did in Entropy. We followed that up with a sort of mea culpa where I pointed out, well, there are some important details here that we glossed over. I really want to revisit Entropy, and Brady's going to indulge me, which is great. Well, he might and might not. A lot of it stems from this. The work of this guy is a guy called Frank Lambert. And notice it says disorder, a cracked crutch for supporting entropy discussions. So every time you hear entropy mentioned, or the vast majority of times, and certainly as undergraduates, and certainly in that 60 Symbols video, we do the same thing. We make this link between entropy and disorder. For a person who isn't a scientist, even for a person who is a scientist, that's actually a very difficult and very confusing link to make. Because, for example, the argument is that, entropy is always increasing, disorder is always increasing. How does this happen? So this is from a kid's crystal growing kit. So we get crystals. How do we get lovely structures like this? Beautiful structures. This is a crystal structure of silicon. And we can get this extended over, huge pieces of silicon. How much more ordered do you want to get? And yet the argument is that disorder is always increasing. How then do you take, atoms in a melt, or atoms in the gas phase, and this is how we grow silicon, they're pretty disordered, you'd argue. And yet they hit the surface, and they grow, and they build, and they form this structure. So that seems to be, on the face of it, pretty good example of something which is very disordered turning into something which is very ordered. That's the issue with using order and disorder to explain entropy. And this is something that this guy Lambert has been banging on about for quite some time, and quite rightly banging on about, because it's exceptionally misleading. I'm going to cover just very briefly two aspects of this. You could then quite rightly ask me, well, how does it happen then? Does this break the second law of thermodynamics? The fact that you're seeing this apparent disorder to order transition instead of the other way around? Have the laws of thermodynamics suddenly gone wrong? Have I misunderstood everything? The important thing here is you've got to take into account the entire system. You've got to take into account whether the system is closed or open, if there's energy or matter flow, all of those different things. We can even reduce it further to make the argument of this even simpler. The important thing that we're neglecting when we talk about, just the atoms forming an order disorder is what's the role of energy. And in particular, when those atoms bond, they give off heat energy. And that heat energy is an exceptionally important contribution to the, I'm going to use these, disorder of the system. We've got to take the whole system into consideration. Also, if you take the whole system into consideration, there is nothing saying that over here, entropy can't go down, as long as over here, a lot more entropy is produced, and the net value of the entropy goes up. But the problem is, in many cases, particularly when it's put across to a sort of general public, a general audience that may not have years of undergraduate or postgraduate experience with thermodynamics, for example, many times disorder is just taken as, well, this is ordered, and lots of our molecules in the gas phase are disordered. That's really damaging, and it's why Lambert says here, disorder, a cracked crutch for supporting entropy discussions. What I want to talk about is the work actually of a really impressive group in Michigan. We had a guy called, sorry to put so many papers, but I've really got to give credit where credit's due. This guy, Dane Frenkel. So Dane Frenkel is a physical chemist in Cambridge. He's done a lot of work, very important work, very insightful work on these type of issues in terms of phase transitions, order, disorder, entropy, something called enthalpy, energy, etc., all these type of things. He gave us a wonderful colloquium a couple of weeks back. And I sat there, listened to that colloquium, and feeling even more guilty about that entropy video we did a while back. He really sort of, motivated me to examine this again. And one group's work he mentioned a number of times is Sharon Glotzer's group at the University of Michigan. Her group does really remarkable computer simulations which show that purely from entropy alone, throw away the energy consideration. So what you can do in a computer, it's very straightforward. Oh, we'll use these. Two molecules, right? In real life, and we'll talk about this later, Brady, in real life, those two molecules will attract each other, okay? You can't get rid of that attraction. They will always attract each other if there is nothing surrounding them. You can put them in a solvent, and you can tune that solvent so you get rid of that or minimize that attractive interaction. In a computer, what's great is you can just turn it off. And so they get rid of the energy term, and they're left with just the entropy term. And we've got it again for the pedantic 60 symbols viewers. I know there's a difference between free energy and energy, etc. But we're just going to think about the attractive interaction there. We're going to turn on the computer simulations, they turn off that attraction. They turn off that potential energy contribution, and they just focus on the entropy. So what we've got are what are called hard spheres. And it's the most elegant example of where entropy can produce order. And I got in touch with them yesterday, said we were probably going to do a 60 symbols video on this, and they got back in touch really quickly. A guy called Michael Engel sent me some videos of the work they've done, and it's really quite neat. I'm just going to show you one of those videos. So what's happening here is that the green bits are the ordered regions, the red bits are the disordered regions. And what you can see, a function of time, as this thing proceeds, it gets more and more ordered, purely due to entropy. And you might say, hang on, how does that work? How is entropy driving this? This seems to go entirely against the conventional idea.
I've got a bigger question than that.
Okay, yeah.
What's the difference between an ordered sphere and a non-ordered sphere? They were just a bunch of spheres in a box.
No, but it's the relationship of the spheres with each other, the positions of the spheres with each other. So you can look at something called correlation function, and you can see how one sphere is related to its neighbours, and you can use that to work out the degree of order. It's something called an order parameter.
So that thing kind of ordered itself, like a beehive.
Exactly. That's it. It ordered itself just due to entropy. So this is why this idea of associating entropy with disorder is really misleading from a number of perspectives. So what is entropy? Right, so I wrote this down at the start of that video. So entropy is Boltzmann's constant times the log of W. What's W? W is the number of microstates. Sharon Glotz, in a wonderful TEDx video she does, actually just says, well, let's just call W ways. And W is the total number of ways you can arrange the molecules in a system. So if we've got, where's the trusty balls again? This is why entropy is generally associated with disorder. Because if we've got, oh, I really need a box. Right, just to keep them in place. That's all the box is there for. The important thing is, there are very, 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 very many more ways of organising these molecules so that they're disordered, so that they're spread out, than there are of forming them in ordered structures, right? That's the essence of entropy. It's the fact that there are so many more ways of spreading the molecules out than of clumping them together, having them in an ordered structure. However, what Glotzer's group do, and this is really clever, and others have done it before them, but there's something very, very elegant about Glotzer's work. What they do is that they set the system up so that there are more ways for the spheres to be ordered than there are to be disordered.
Is that by overcrowding? Because their box looks very crowded.
Exactly. There's a key aspect of the what's called hard sphere interaction. So they're crashing into each other and bouncing off. That's very, very important. That's a very important aspect of it. And getting computer simulations are great because you can just switch off the parameters. Actually getting it like that in real life is very, very tricky. But as I say, groups have done it in the past by controlling how the particle, well, trying to switch off the potential energy between the particles.
I mean, they're just they're loading the dice beyond belief. Let's talk about nature. When that crystal forms in my solution or on a surface out of the gas, are you saying it was more likely to happen? Like there were more ways it could happen than not happen? Or was that different?
So the important thing there is you've got to take the whole thermodynamics into consideration. There's the entropy term. Sorry, Brady, it's not going to be, I'd love to give you a straightforward answer, but it's not. We have something called the free energy. And what we've got to do is take into account the potential energy between these, so how much they want to sort of stick together or bond together. That's one term. And then the other term is the entropy, and it's actually an entropy multiplied by the temperature, so temperature plays a key role. So it's the balance of those two things, the balance of the energy, or what the chemists call enthalpy, and entropy, that really dictates how things go. And it's even more complicated than that, because that's the thermodynamics. You've also got to take the kinetics into consideration, but that's a whole other video.